Super. Well, thank you very much for the invitation. It's great to come and talk to you all. So essentially, what I'm going to be talking about, what my research focuses on, is the intersection of machine learning and geology and geomorphology. So the sort of holy grail for geomorphologists like myself is to be able to use these pattern recognition and machine learning detection systems to make the kind of geomorphological maps that is our bread and butter when we're trying to understand the processes that have shaped the surfaces of the various planets in the solar system. And this is of particular interest at the moment because the ExoMars mission will be landing on Mars in 2023. And so a lot of work at the OU and in the UK and Europe generally is at the moment feeding into kind of characterizing the area where that probe is going to land and really understanding what the landscape's like there, how it's formed, and the different kind of hazards potentially that our rover could encounter when it's in situ. So to do this, we want to use the highest resolution data available. And for Mars, that's the HiRISE instrument on Mars Reconnaissance Orbiter. This maybe needs no introduction, but it's a 25 centimeter pixel camera. There's more than 71,000 images. There's probably even more than that actually since last time I updated these slides. And these images are spread fairly sparsely over the planet. So in our landing site, we've got relatively good coverage of the 1 sigma ellipse, so the area where the rover is most likely to land, and sort of fairly good partial coverage over the 3 sigma ellipse, the sort of area where it's improbable that it will land, but it might. This is good from a coverage point of view. It means that we can dive down into this really high resolution data and in great detail look at the kind of terrains the rover will encounter. So like these fractured areas over here, this yellow square is 128 by 128 meters, which is the size of the swatches, the framelets, which we've been using as our training data set. So this is one of those, the training frames, which has gone into feeding our machine learning system. So that's the pros. We have more data than ever before coming back from MRO. The cons is that it's becoming very challenging to actually interrogate all of that data. We have this huge several 100-kilometer area that in theory the rover could land anywhere within. So how do we actually map that area within the fairly short amount of time we have until ExoMars lands? That kind of thing traditionally requires a lot of effort or a very large team. And both of those approaches are being taken. But we figured that why not give machine learning a go? And today I'm going to be talking through some of the results we've got with that system. So effectively the aim, as I'm sure I don't need to tell the audience here, is to extrapolate from a relatively small amount of labeling and mapping done by expert geomorphologists and translate this into a much larger area where hundreds of images can be automatically processed. So that's the holy grail. This requires an interdisciplinary approach. I myself am very much on the geomorphology side of this. Our colleagues in industry at CISIS are the computer science team. So my talk is going to be focused on how we as geomorphologists translate the questions that we would ask of the landscape into terms which we can then give to a deep learning network rather than the specifics of the architecture of the deep learning itself. So I probably don't need to introduce what a deep learning convolutional neural network is, but in brief, it is a computer model designed to learn from a set of examples. The model architecture has many layers, allowing it to generalize and learn hierarchical classification schemes, and it's convolution filters that we're using to do all the things from the edge detection up to the detection of fairly complex landforms. So when we're considering this as geomorphologists, we have to think about the scope of the question that we're asking. And ideally, some of us would like to sort of say, oh, well, can the computer do all of the work for us and put us out of a job? And it isn't there yet. There's no way to really train a computer model to develop the understanding of geology to see how the landscape has kind of been shaped by different processes over the course of geological time. So what we have settled on is a very much a morphometric approach, where we are treating it as a pattern analysis, a pattern recognition problem, and effectively trying to triage our data set using these kind of very descriptive morphological categories, in the hope that that then sort of speeds us up to the point where we can start doing the interesting interpretation stuff. But that interpretation is still very much a human problem being tackled by the human experts using this classification as our sort of first step in that process. So it's not intended as a sole arbiter of terrain, and it certainly isn't intended as a sole arbiter of hazard that the rover might approach. So we have several objectives. Landing site hazard assessment is the primary one, but actually we're already using the results to examine the aeolian environment of Oxia Planum and how the various bedform classes that we've mapped have developed. We wanted, as I say, to do a proof of concept. And then our final technical objective, which is the one I'm mostly going to be talking about today, is transferability. The question arises, we've trained this model in these two sites called Morphalis and Oxia Planum, both of which are located in the Arabia Terra region of Mars and were candidates for the ExoMars landing. We now know that it's going to land at Oxia Planum. And what we want to do is see whether this training, this classification, can be applied to other regions of Mars. And there's some very important reasons that I'll come back to later for why we want to do that. So we've defined our classes in terms of a broad texture. We want to basically come up with a hierarchical classification system where there are two levels. There's a descriptive level, which is what the machine learning is actually going to be using to distinguish between these different features on the Martian surface and make those determinations. But then we want to be able to group those descriptive classes into more interpretive groups, which we as geomorphologists can use to understand what the data is telling us. So we settled on 5 key interpretive groups, which are the sort of 5 most basic landform types that are found within Arabia Terra and Oxia Planum in specific. So these are non-bedrock terrains where we've got kind of loose, consolidated material. It's generally quite smooth at the high-rise scale and is often kind of flat and low-lying. We then have bedrock textures, which are much rougher, much more pronounced relief, and more kind of jagged rocks, fractures in many cases. We have 2 different size domains of aeolian bed forms. So these are features where the wind has kind of come in and moved loose granular material, sand, Martian dust, and shaped it into ridges and wrinkles on the surface. So we're looking at those both at a large scale and at a small scale. The cutoff being about 5 meters across a feature. And that distinction is mainly important because the large ones and the sort of distributions of the large features and the small features are somewhat distinct. And then finally, and quite important for landing on another planet, we have block fields. We want to know where all the jagged boulders are that we really don't want to drop an expensive rover on top of. These groups were then subdivided into 14 ontological classes, which I'll show you some brief examples of here. So we have 3 non-bedrock classes, which you can see or I hope you can see very small examples here. For each of these, what we wanted to do was look at what was on the ground, the different terrains available, and kind of pick out a few end members and really constrain what range of features were going to be going into a class, because a real landscape, nature doesn't like the sort of discrete boxes that we need to use for this kind of study. So we had to make sure that we're making our boxes broad and general enough that pretty much anything that the machine learning system encountered would fit into one or other of these boxes. So broadly speaking, this section of the ontology is an ascending roughness scale. We have the very smooth, featureless, non-bedrock terrain is our smoothest, and then this gets gradually rougher throughout the non-bedrock. And then the bedrock textures are much rougher again, going up to really rugged and fractured things at the top of the scale. And we found that approach worked quite well for dividing up this continuous sequence. Our ripple classes then basically were tailored around whether the ripples had a simple form or a rectilinear form on the large scale, and then at both scales whether they were continuous or discontinuous. And it was quite important to know what type of substrate some of the discontinuous ones were overlying. Boulder patches had the fewest classes because there's less to say about them. They're all effectively randomly distributed, and while there are variations in density, that isn't too important for the questions that we were asking. So we took loads and loads of little squares like these, and I spent an inordinate amount of time going through and drawing around the areas of these images which conform to one or other of these ontologies. And in the end, our colleagues at CISIS fed them to a machine learning system, and we got output which looks a bit like this. So here we see a small impact crater in Oxia Planum, and the interior is filled with this, this array of large simple form ripples. The edge of the crater has been picked out quite nicely as a block of rugged bedrock terrain. And there are these smaller patches in beige which are marking out areas where smaller ripples at or near the resolution of the image can be found. One quite interesting thing is we asked it to tell us the difference between the isolated ripples and the continuous ones. And within this patch, which as a human you might look at it and just draw a big circle around it and say it's all continuous, but it's actually gone down at the meter scale and partitioned all of these features into which bits it thinks of the ripple are isolated and which are continuous. So that was a really interesting result. Sort of not the way a human would assess this landscape necessarily, but it's definitely not wrong, and there's a lot of value in what it's returning. So when presented with lots of areas like this, we have to figure out how reliable this is. And at first glance, these images look really good. We're very pleased with the way it's finding the bed forms. And as I say, my colleague Eleanor has already been using that output for further more science-based research. We calculated precision recall and intersection over union by comparing our validation framelets to my original labels, and found a value of around 74% for the the mean IOU for our full 14 classes, which isn't bad but isn't ideal. When we combine them into the interpretive groups, the way we're largely going to be using the data, that improved to 92, which was a number we were a bit happier with. However, we felt there was a bit of a disparity between what the statistics were telling us we found on the pixel scale and how the data was looking and how usable we felt the data was at a landscape scale. So we wanted to very much assess how reliable is this really? Is the data actually more useful than those stats are suggesting? And to some extent we could do that by comparing the precision and recall and looking at which ones were higher for which classes and what that told us about how it was confusing them. But we also wanted to take more of a geomorphologist's approach and actually not worry about the pixel level data at all, but instead compare our data to observations. Now, ideally, to get this kind of ground truth assessment, we would want wheels on the ground, and our rover hasn't landed yet. So this is where we come back to that theme of transferability, because NASA have some wonderful rovers on different parts of Mars. So we wanted to see how well our data would perform if we ran it on Jezero Crater and Gale Crater instead. Gale Crater, we did some initial looking around and decided there were too many features which weren't included in our ontology. There's things like dark sand dunes which just aren't present at Oxia Planum. So we ruled that one out and instead focused on Jezero Crater, landing site of the Mars 2020 Perseverance rover. So here is our classification map with both the descriptive classes and the interpretive groups for the full area of Jezero Crater. So here's the fan, which you may have seen lots of photos of. So the ancient river system kind of flowed down here into the crater and deposited this huge alluvial fan, which is covered with boulders. And you can see that those have been picked out quite well in black, while the sort of more rugged areas are highlighted in blue. And then you have these sort of flatter, low-lying areas have a far more prevalent amount of green, which is indicating our non-bedrock classes in this assessment. The blue areas showing the different dune fields, or sorry, not dune fields, ripple fields, around the edge of the fan and out here into the crater interior are really nicely picked out in blue and yellow. So this gives us quite a lot of confidence in the results of our model and shows us kind of a similar level of reliability to what we were seeing in Oxia Planum, which is very encouraging. We can also go down and look at the rover's eye view of what's going on in these areas. So this is the track of the Perseverance rover between Sol 13 of the mission and Sol 66. And you can see here purple indicates fractured bedrock, while yellow are the more rugged, rough areas. And we were quite interested to see that at one point it was trundling happily over a fractured area, went slightly into a rugged area, and then seems to have just turned around and backtracked, suggesting something about the traversability of those features, perhaps. There's a few areas where it's made short crosses over less extreme bits of rugged terrain. And if you look at these mastcam images, you can quite clearly see that we were initially quite worried when we were coming up with this ontology that these these areas look quite steep, quite unpleasant. But actually you can see that these are solidly filled with non-bedrock material between the fractures, and so a rover should have no difficulty traversing this. I'll quickly show you some images from the Ingenuity helicopter, because it's amazing that we now have air photos of Mars. So here you can see the helicopter is flying this way across this classification, and the rugged bedrock we can identify quite clearly in the air photo compared to the non-bedrock material here. We can look at another area a little further north where we can pick out areas of smooth and large ripples on either side, and this does correspond to what is being seen here in the classification. Finally, in this area, towards the end of this ninth flight, again we see another big patch of rugged bedrock about where our model suggests it should be, interspersed with smaller patches of non-bedrock material and these black boulder fields, which are again visible in the in situ images. So this gives us a lot of confidence in what we're doing. Finally, because this area has been studied in a lot of detail, we can compare to a human-made map of this site. So this is the work of Stack et al. And the Perseverance team, who before the rover landed made a really detailed map of the geomorphology of the site using high-res images. We've translated their map into the color scheme of our interpretive groups. So where they haven't found any superficial unit, we've interpreted that to be bedrock. Where they've found undifferentiated smooth material, we've interpreted that to be corresponding to our smooth non-bedrock terrains. They have very similar classes. Their cutoff between large and small aeolian ripples isn't quite in the same place. And then they've defined talus slopes, and a lot of our boulders are found in talus slopes. So we've colored their talus slopes in the same color as our boulders. And what we found is a product which is impressively similar. The human-made map is a bit more clear, it's a bit crisper, because our model has gone right down to the pixel scale and found probably more detail than is actually needed, and perhaps more than is actually there. A lot of these sort of small-scale variations may just be noise. But still, we're quite pleased to be able to look at these two datasets side by side and see just how similar they are. So I will leave it there. Thank you very much for your attention.